we've talked about the k component of the curl. The other big definition we have to get to before we we state Green's theorem is the divergence of a vector field. So here's the definition. The divergence of a vector field f is mi hat plus nj hat is you take the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y, and you add up those partial derivatives. Let me just point here, this is a scalar quantity. It's always useful to emphasize what's scalars, what's vectors here. So this is a scalar quantity. Sometimes the notation that I will use for this will be del dot f. These are two different notations for the same thing. Okay, so we can use this, computationally speaking, compute the divergence of f is equal to x e to the y, x squared y squared. So the divergence of f is equal to the partial derivative of the first component with respect to x, so that's e to the y, plus the partial derivative of the second component with respect to y, and that's going to be 2x squared y. So for the divergence, you take the partial derivatives, corresponding partial derivatives of each entry here. You take the x partial derivative of this, you take the y partial derivative of this, and you add up those partial derivatives. There are some nice physical interpretations of this, and something I just want to kind of say here. Let's think about f on this slide as corresponding to a fluid flow, like, for example, a gas. And as it turns out, the divergence will tell us, is our gas expanding or contracting? So here's what the answers are. If the divergence of f is positive, this would tell us the gas is expanding. If the divergence of f is negative, this would tell us the gas is contracting. And if the divergence of f is equal to 0, it's neither expanding nor contracting. So expanding would be like you have an explosion. So, if you have an explosion right here, gases are very, very, very quickly going to move away from the explosion, and so the divergence there would be very positive. If gas is being sucked in, due to contraction right here, the divergence would be negative. Take a look at this picture. This should look familiar. It's the picture that I drew at the start of section 16.2 for this vector field right here. Let's calculate out the divergence here of this f, for f is negative y, x plus y. It's the x partial derivative of this, which is 0, plus the y partial derivative of this, which is 1. So it's 1, so we are in the expansion case. And I think that we can kind of see here that there is some expansion going on, that the arrows are moving away from the middle here. They aren't moving towards, they aren't moving inwards. They're moving away. There is a bit of expansion going on. Let's calculate out the divergence here in just a couple of basic examples. So for this one, the divergence of f would be the x partial derivative is 1 plus the y partial derivative is 1 is 2. And so that would be an expansion is also occurring here. For this one, the divergence is going to be the partial derivative with respect to x is 0. Partial derivative with respect to y is also 0. So this is a nothing, this is a no expansion or contraction going on here. If we were to draw this picture, this would be, let's see here, like for example, the point 1, 0, with a vector like that. You'd have the vectors are like this, things are just kind of spiraling around. Maybe let's just do, you know what? I think that's good. This is enough here for divergence.